Welcome to section 12.1, day 1, one and two-sided limits. Today's objectives are to estimate limits graphically, and we're going to use one-sided and two-sided limits to do this. So recall from chapter 1, we looked at end behavior and continuity using limits. Today we're just going to look at limits in a general sense. We're going to estimate the limit as x approaches 4 of x squared minus 16 over x minus 4. We're going to use a graph. In your book, it'll say support your conjecture using a table of values, which is what we did back in chapter 1. I am not requiring a table, although often you will have to use a table to figure out what the limit is. Here, when we look at the graph, we're going to approach 4. And the way we do this is we want to approach both 4 from the left and from the right. So as we're approaching x equals 4 from the left, we're going up this line. And as we get to 4, we get closer and closer to this value where the hole is. We don't care what's actually happening at 4. We just care what's happening as we get really, really close to 4. So as we're coming in from the left, we are approaching, this has a scale of 2, so we're approaching 8 as we come in from the left side. If we come in from the right side, we're also coming down here, and we're also approaching that same hole from the right side of our graph. So when we do this, both of them are approaching the same value. We say the limit for this one as x approaches 4 is 8. So our limit for this one is 8. And our table shows this. As you see, as we're coming in from the left, we have 7.999. There's nothing at 4 because there's a hole there. And I have 8.001 on the right side. And they are both converging on 8. Like I said, we don't care what's happening at 4 itself. We just care as we get closer and closer to 4 what is happening. All right, so one of those things with limits is that limits are independent of function value at a point. So it doesn't matter what the value is at x equals something. What matters is what are we approaching as we get closer and closer to that x value? What y value are we getting close to? So even like this shows on this thing, we have where c is on the left graph, it's undefined, there's a hole there. But both of our lines or curves coming in from both the left and right are both approaching that same hole. They're both approaching that same value. So we have a limit as x approaches c of f of x is L. We use L for limit. It's some number. The middle one has an actual value for when c, whatever c is for our x value. We actually have a dot farther up. Well, we don't care what the actual value is at c. We just care that the two graphs, as they come in from left and right, are approaching that same hole, that same value. So even though we do have a value for c and the value is n, we don't care about that value. We just care where we're approaching. So our actual limit still exists, and we're approaching some value L, which is on our graph. And then we also have times where on our graph the whole function is defined, and there are no holes, there's no gaps, and then our limit is just what the value of c is. That happens also. Quite often, though, when we do graphs, we will find that there's holes or there's jumps or something going on where we're trying to find our limit. Well, first let's do left-hand limits and right-hand limits. So what I was demonstrating on the first slide is that we were coming in from left and right sides on our graph into some x value, and we're trying to see what we're approaching. Well, we can denote these, if we're doing left-hand limit, we denote that by a negative sign. So you'll see this as limit as x approaches c from the negative of f of x is L1. And it's read as the limit of f of x as x approaches c from the left is L1. And if you think about this, on a number line, our negatives are on the left, our positives on the right, and this is why we use this notation. For a right-hand limit, we're going to use a plus sign. If the value of x approaches the unique number L2 as x approaches c from the right, then we show limit as x approaches c plus of f of x is L2. So we can do a couple of different things when we do limits. We can do a left-hand limit, we can do a right-hand limit, or an overall limit. When we do an overall limit, the limit from the left and the limit from the right as we approach some x value have to be exactly the same. So like it says on the bottom, The limit of a function f of x as x approaches c exists if and only if both one-sided limits exist and are equal. They have to be the same. So as long as your limit as x approaches c from the left, f of x equals the limit as x approaches c from the right, f of x, and they both equal the same value, then we can say the limit as x approaches c of f of x is this L. So both the left and right hand limits, both the left and right hand parts of the graph as we approach some x value must approach the same y value from both sides. Here's a graph that we have, and it says estimate each one-sided limit or two-sided limit and tell me if it exists. So the first thing we're going to do is we're going to do the limit as x approaches 1 from the left of f of x. And if you look in your graph, we're going to be looking at this part of the graph as we're approaching 1. So we're coming in on our x, we're getting close to 1, and this is our y value we're approaching. And we are approaching -2. Okay? If we're looking at the limit as x approaches 1 from the right of f of x, we're up here, we're getting closer and closer to x is 1, and as we do it, we're getting close to this y value. And that y value there is 3. So we're coming in from the right, we're coming in from the left, that's what you show these little arrows here, all right? We're trying to see what we're coming in from both sides. All right, since these two limits do not agree, they are not the same exact value, that means we do not have a limit at x equals 1 because they are going to different y values. So there is no limit there. It does not exist. And I tell you to answer this. Here we have another graph. This is a piecewise function. We have x squared minus 1 when x is less than 1. We have 1/4 x minus 1 when x is greater than or equal to 1. Here we're approaching 0. It says the limit as x approaches 0 from the left of g of x. So we're coming into 0 from the left. And you'll see the arrow here again. We're coming in, we're following now, we're getting closer and closer to 0 from the left side, and we're approaching this y value, which is -1. When we come in from the right, we're coming down this line. As we get closer and closer to 0, we're also approaching that same value of -1 for our y, which means our two limits agree. So then we say the limit as x approaches 0 of g of x is that value, -1. Because the left and right limits agree, the overall limit as x approaches 0 is -1. Today when you do this, you're going to be given some equations. You're going to put them in your calculator for your y equals. You're going to look at your graph to see if you can figure out the limit. Quite often you'll be able to see what the limit is by looking at it, or you can do a trace function. You can find the value. Quite often though, you will need to use a table to look at. I'm going to show you that here on the next slide. So here it says, find the limit of the following. It says the limit as x approaches 3 from the left of x squared minus 5x plus 6 over x minus 3. I type this in my calculator for y equals. You notice I have parentheses around my numerator and denominator. Make sure when you're doing division, you have your numerators and denominators in parentheses, or you'll get a wrong graph. On the bottom left is the graph of this equation, and it looks like, if you look at 3, positive 3, coming in from the left, it looks like we're getting close to 1. Now, quite often you won't be able to tell for sure what the value is. So what you do is use a table, and you'll notice I set my table up, I'm trying to find around 3. So I use my table set as 3, I use my delta on there as 0.1 or less, so you can see what's happening. And when you look at your table, you'll see as you're coming in from the left side, which is a 2.6, 2.7, 2.8, 2.9, we are getting closer and closer to 1. At 3, there's an error, which means there is a hole there. And then as we get past 3, it goes to 1.1, 1.2. But as we're coming in from the left side, we are getting closer and closer and closer to 3. So the limit on this, as we get closer and closer to 3 from the left side, is 1. We're getting closer and closer to 1. On this one, both the left and right side limits agree, and we would have actually a limit at 3 of 1 also. But this is just asking from 3 from the left. You will have to use your calculator today to do these. I would recommend quite often using a table to see if, when you're coming in from the left and right, if they agree when you're trying to find a general limit. This is what you're going to be doing today. You do not need to make any tables, but you will need to use tables off of your calculator to see where your limits are. That is all for section 12.1 day 1, using graphs to find limits. Thank you for watching and have a nice day.